This is a video about my misadventures in trying to build a homemade hypocycloidal gearbox for use with a 5-axis trunnion table. Most of the problems I had were due to compounded error, trying to use Cartesian coordinates, X, Y only movements to make my parts. First thing I learned I had to have was a fixture to hold the parts for rework, because working with the tolerance I was trying to get, I was having problems getting low tolerance parts so there would be low backlash. So I built a fixture that has holes in it for dowel pins, so I could try and orient the parts as close as possible to the original position for rework. This is the first gearbox I built here. This is the output drive. It fits inside the pocket here, and there's no bearings or anything in it, so I didn't really like how much friction and stuff there was and slop. So then I built this one, which has a bearing in it to stabilize everything, and I built it with an insert of the cam profile so I could experiment with different materials and gear ratios. One thing I should note is when I was using the fixture, I also used limit switches that were hooked to Mach 3, and it wasn't that accurate because I changed the speed at which the machine approaches the limit switches, and that had a huge effect on how accurate they were, and they still weren't perfectly accurate even when I kept the speed the same. So I had to just forget the limit switches and use a dial indicator to locate everything each time I started things up for the day. The problem with this one was it was getting pretty tall and eating up a lot of my Z travel because of the thickness of the bearing and everything, and then there was a big 5-inch long servo motor hooked to the back side of it, and so it was getting pretty large. I tried experimenting with some different plastics, trying to preload them to get rid of backlash, but that didn't really work that well, because when you get a big 10-inch diameter disc on the end of it and put some force on it, you could see the springiness where the pins were, or cam profile was being distorted or compressed by the metal parts. So that idea didn't work out. The other thing I learned real fast was when you're putting these things together and running them with low tolerance, you got to make sure they're real clean. One little metal speck will cause big problems. On this one, the cam got all galled where it was rubbing against the profile here. These teeth and this where they rubbed just galled up terrible. The other thing was the gear ratio on the first two I built were 20:1, and with a big table hooked up to it, you put pressure against it and it would actually backdrive the motor a little bit, even with the gain turned up on the amplifier. The last one I built with a rotary table instead of just relying on X and Y. So that worked out a lot better. I used the rotary table along with X-axis to machine the profile and teeth, and since the the, the the profile of the teeth, the very top and the very bottom, get machined away for clearance. So when the axis would move back and forth, the dwell marks due to the backlash compensation stopping for a second were all situated at a spot on the cam profile where they'd be machined away later. And it was a lot easier keeping everything concentric with the parts made on the rotary table. Any errors in the x-axis were just translated to a slightly different diameter in the parts being made. So it just worked out a lot better using the rotary table. The rotary table I used was a 8-inch Enco, and they have their problems. The thing seized up after about a day, and when I tore it apart, I could see that it wasn't adjusted right axially, and it had a lot of grit in it from the manufacturing process. They hadn't cleaned it very well before they put it back together. So I adjusted it and cleaned it up, and got that part of it working. But then when I started measuring things, both in the horizontal and vertical position, the mounting surfaces weren't parallel and perpendicular to the tabletop. So I had to figure out what size shim stock to slide underneath it when I clamped it down. But I got that done, and then finally made some parts that I would consider usable. This is the fixture I used on the rotary table to locate all the parts I was making, so I could get them centered again, doing rework, and make that a little easier. The Enco table, my main problem with it is that it is very leaky in the vertical position. They suggest using a lightweight oil for it, but I used 90 weight just to see if it would leak out a little slower, and it did leak out a little slower, but it still makes a heck of a mess. If I had to do it all again, I think I'd probably try making this part of the table with the worm drive instead of a hypocycloidal, unless you've got really expensive and accurate machinery. It's really tough to do. I have a Chinese Bridgeport copy that I've mounted precision ground ball screws in, and still the best I could get as far as backlash and XY goes was about 1/1000 of an inch, and that's just it works out to be a problem when you're making precision parts. So I guess that's about it. The next thing I will show will be the insides of the final gearbox I built. This is the final gearbox that I machined, and instead of machining an outer cam profile, I drilled and reamed 41 holes and then Loctited dowel pins into them. It's a 40:1 gear ratio, and everything was manufactured on the rotary table, so everything is as close to concentric as I can get it. This is the offset cam. It's offset about 32 thousandths, I believe, and these are the output pins. That match up with these pins here. That gets mounted on there like so. see, I'll run it now, and the speed will be about 3,000 degrees a minute. I used a coreless disc motor for the motor on this axis because it has a very low profile and it doesn't stick down any further than the edge of the table when it's turned to the side. Just sitting in the holes, it's not being constrained by any bearings or anything. And it is turning 40 times slower than the input. This is the part that constrains the output disc both axially and radially. This just fits over this part like so, and there's locator pins that keep it aligned with the screw holes here to hold it down. The output disc gets held in by this surface on the inside, which mates with this surface here, and then on the output table, the outside of the containment plate here rubs on the underside of the turntable, which has got it's a high density plastic insert set down into it, and once that part's on there, these screw holes here just screw into the HUD here and secure it.